Okay, so this is a crash course on bending and shear moment diagrams. Let's get the sign convention established. I'm not going to be talking about rotations and deflections. We'll just talk about internal forces. So we need to say that, well, any distributed load is positive going up. I'll call this W. My shear goes up, comes down for positive. So it depends on the side. Positive shear is up on the left side. Positive shear is down on the right side. Okay. You define it like this, then everything works out. Don't define positive as up, depends on the left or right. Okay, my moment. Same thing. Depends on the sign. Or side, sorry. Goes like this on the left, clockwise, anti-clockwise on the right. Both positive. Okay, so clockwise is not always positive, depends on the sign. Okay, another way to remember this is it tends to bend it like this. You can see that these forces are trying to bend it like this. IE is concave up, that's no accident. Okay, if I draw a little piece there, then I can see that this is in compression and this is in tension. I will mention this though. This equation. This is Y. Y is the elastic curve, i.e. the deflection. Okay, double prime means concavity. Okay, so the concavity of the deflection is dictated by M over EI. EI is positive. So the sign of the concavity of the deformation is the sign of M. Positive M, concave up. Okay. Likewise for negative M, concave down. Okay, I'll just mention that since I might use that. I'm not really going to be talking about that, but that's useful information to have. You can sketch the deformation and figure out where, if the moments are positive or negative or zero, depending on the concavity of your sketch. Okay. The relation between them, W, V, and M. Okay, I think I'm going to skip this derivation. Are as follows. Okay. First of all, W is the slope or the first order derivative of V. Okay, I'll just call it V prime. V is only a function of one variable X. So prime indicates first order derivative. Your double prime is second order derivative. Okay, and V is dm dx. Okay, V is the slope of M. Okay, two useful equations. What else do we get out of this? Well, you can integrate both sides. Okay, let's take the integration of W first. Well, let's write it out like this. W dx is equal to dV. Let's integrate from XA to XB. XA to XB dV Okay, so the right-hand side, we know this is going to be the antiderivative. Okay, v at xb minus xa. Okay, this is the first lemma of calculus, fundamental theorem of calculus, I think it's called. Okay, so what does this mean? Well, the integration is nothing but an area. Okay, so the left-hand side, this means the left-hand side is the area under the curve of W. Let's just write that out. Okay, integration is nothing but area under the curve. Of W from XA to XB, i.e. the area between 2 points, is equal to V XB minus V XA. That's just what we've written. So this is going to be the net change in V from XA to XB. Okay, very useful formula. Let's put our useful formulas up in a box. We're going to be using them a lot. Okay, our first thing, W is B prime. And our second thing is I'm going to denote this in shorthand what I've written there. Okay, the area under W is going to be the change of V from A to B. Okay, our second equation. I'll leave it here. Okay, we're going to integrate on both sides. Okay, I have V dx from XA to XB is equal to dm XA to XB. Okay, just integrate both sides. Therefore, this is going to be m at XB minus m at XA. So I can get a similar formula there. What does this mean? We'll be quicker now since we just did this. This is the area of B, from A to B. It's going to be a change in M from A to B. Okay, so our second set of formulas that we'll be using, I can write it succinctly like that. Okay, I'll put them up here. W is V prime, and V is M prime. I've got, what do we have? Delta VAB is equal to the integration of W from A to B. Delta MAB, this is what we just did, integration from A to B of B. You'll see why I'm not being very concise with the notation, because I'm going to treat these as areas. Okay, these are nothing but area. Let's be a little more concise. These are nothing but areas under the curve. Okay, we're going to use that a lot. Okay, so who cares? All right, I want to draw the bending moment diagram. Maybe I cut it. Here's my guy. And I cut it at some location. Oh, yeah, okay, I'll do the, sign convention, all that stuff. I'll write sum of moments, sum of Fy. I'll get V of X, M of X, and I plot it. Why not? Well, you're going to get a headache doing this. You should know how to do this, but It's not necessary. Let's say 97% of the time. Okay, this is too much work. Don't need to do that. 97% of the time. Don't need to do any equation writing. All right, if I did that, if I write m as a function of x, I'm gonna have to start evaluating it in places, figure out how to plot it, all that stuff. It's much easier way to do all this. Okay. So these are useful formulas. Some other consequences. Let's look at this. W is V prime. We'll be using these a lot though. W is V prime. So let's look at some cases. W is 0, then V prime is 0. Therefore, the slope of V is 0. Okay, how should I draw V then? Flat line. Right, something with 0 slope is just a flat line. Let's take another case. W is constant. V prime is constant. Okay, slope of V is constant. That means it's a line, straight line, going up or going down, straight line. Okay, you can keep going with this. So I'll up it one order. W is linear. Right, you can also see over here, W is linear, V is going to be quadratic. That's why if I have 0, I'm going to get a constant integration. Constant, I'm going to get a linear term. Linear, I'm going to get quadratic. Right? If we integrate, we're upping the order. So if W is linear, then I know V is quadratic. And you can keep going if you like. Quadratic. V is cubic then. And so on ad infinitum. So this gives us a sense of, well, not a sense, this gives us the shape of this guy. Okay, we'll come back to that. Likewise, you can do the same thing. All right, this looks very similar. V is m prime. So I can argue that, well, if V is constant, let's say V is 0, then m prime is 0. So it's flat. Straight line. Let's use the same terminology, flat line. V constant. Right, the other way, again, to think of that about this is, right, upping the order of x here, right? Because I'm doing integration, so it picks up at x. Or you can think of it in terms of slope. So m prime is constant, so it's a line up or down, and so forth. V is linear, is quadratic. Okay, so we'll come back to this. We'll use this. This will figure out. This will show us how to draw the shapes on these diagrams. Okay, so I think I've talked enough about this stuff. Let's use it. Right, we're going to use all this to help us draw some diagrams. Okay, I have some examples here. Let's see. Pull up a simple example first. Okay, here we go. Let's do this. I'm going to need some room, so I'm going to erase this. And we're going to work vertically, basically integrating as we go down. Right? If I integrate W, I get to V. If I integrate V, I get to M. So we're going to work our way down from W, or the level of the beam in general. Okay, I've got a 12 kip here. I've got a reaction, 26 kips here. This is 3 feet. I've got a force here, 10 kips. I put, let's do this proper, 3 feet, 2 feet, 2 feet. The direction here is 4 kips down. Okay, do the statics. These would be the given loads. Do the statics to get this. It's a whole nother story. Okay, so the other thing I didn't mention is if I have a point load actually just causes a direct change in V. Point load is actually a delta function inside of here, and what you get is just the function back. So I won't go into all of that, but I'll just make a note. Point loads cause a direct change in V. In the direction. Okay, it's so straightforward that I'm not going to explain it farther. We'll just see how it works. Okay, so I don't have any W. I don't have to deal with this in this particular example. Just got point loads. Okay, and for the shear, I follow the loads. So here, go down by 4. That leaves me at -4. So I'll put the change here next to the 0. And then the value I end up with, draw it a little bigger, is -4. Okay, what happens next? Well, I should deal with W actually. W is 0, so V prime is 0. So I should draw the slope of V is 0, so I should just draw it as a straight line going across. Nothing happens until I get to this 10. Hit the 10, comes down by 10. I'm going to put that as a -10. And you're going to kind of keep track that now I'm at -14. Okay, how should I draw it up to the support? W is 0, the slope of V is 0, so it's a flat line going across until I hit this 26, then I go up by 27. So up plus 26. And that leaves me, if you work that out, should be 12. That value there should be -14 plus 26. And then finally, for the same reasons, W is 0, V prime is 0, slope of V is 0. So it's a straight line going across until I hit this 12. And then I should go down by 12. And that'll bring me back to 0. Okay, if this doesn't close, you've got a problem with your statics. Okay, so we like to see it close. There are some special situations, I would say, for the moment. If you have an applied moment or so, something like that, then you'll see a non-zero moment there. Other than that, we want it to close. Well, especially for shear, we want it to close. If we didn't do that correctly, then we didn't do our equilibrium correctly. Okay, I should have maybe given myself more room. That's okay, I think I've got some room here. Okay, let's do M. Okay, so now what do we do? Well, I know that I start at 0. Okay, there's no moment here. This is a pin on the end. There's never going to be a moment here unless I put one there. I don't put one there. This example does not have that. Okay, so the moment is 0 here. Not here, not 0 here, by the way. We'll see. But because I've got a pin on the end, I should say, yeah, pin or no applied moment. So over here, it's going to be 0. Put that there. And I'm going to start at 0. Unless I see a mo, I'm going to start at 0. Okay. Now we come to this equation. Okay. The area of, oops, sorry, this one. Okay, so going from V to M, I'm going to start computing areas. I would have computed them here, but I didn't have any W. So the area under the V curve is going to be the change in M. So let's compute those. This is really easy. These are the shapes. So this is -4 times 2 minus 8. Okay, we get a negative area. That's fine. This is -14 times 2 is -28. These are going to be my changes in M. And this is going to be plus 12 times 3, positive 36. That'll be another change in M. Okay, so I know from here to here, it's going to go down by 8. That'll bring me to here, which is -8. How do I connect that? Go to, right? When I talk about the shapes, I'm really thinking about derivatives. So I'm looking at this guy. The slope of M is going to be the value of V. The value of V is negative and constant. If it's negative and constant, then it's a straight line going down. Okay, just to make that clear, V is the slope of M. It's negative, constant, value of 4. All right, so from here to here, I'm going to use the areas again. I'm going to go down by 28. That'll bring me to -36 over here. Okay, you just got to keep track. -8, -28, bring me to -36. Okay, how do I connect the dots? Now I'm talking about shape, talking about the slopes. V is the slope of M. V is negative and constant. It's a straight line going down. Let's do that. This is -14, -14. That's the slope. So just to hammer the point home, V is the slope of M, negative and constant, straight line going down. Okay. Now from here to here, and my change in M is going to be my area of V, which I already computed, which is positive 36. It was up by 36. I have to close my diagram, which is great. I don't see any moment here. I shouldn't have any moment there. How do I connect them? Well, V is the slope of M. It's positive and constant. Therefore, it's a straight line going up. Slope of M is a positive constant straight line going up. And just to hammer it home, my slope is the value of V, which is 12. So I actually know the slopes of these diagrams. Okay, so here I have the bending moment diagram and the shear diagram without doing anything. Well, I had to do something. I didn't have to write out any equilibrium equations. I didn't have to cut this guy. I just used the areas. As I mentioned, there's only a couple situations where I actually have to cut it, even if I wanted to find the moment here. Right? I could figure that out just by geometry if I want. If you want to cut it, that's fine. In fact, it might be better to cut it. But in any case, I've got the whole moment diagram without doing any cuts, right? So typically you might be asked to do this or this. Draw it without doing anything. And I know the maximum moment, which is usually what we design for. We know the moments other places if you want to design other sections. Okay, that's the diagram for that guy. Let's do one with the distributed load. Let's do something real simple. Okay, let's start off crawling and we'll start running. Let's say 2 kips per foot. Let's say this is, let's say it's 10 feet. You can do the statics. This is kips per foot. You can do the statics. Well, what you'll find is that I've got 2 times 10 is the equivalent load. Symmetrical, half goes here, half goes here. I've got 20, half goes here is 10. Half goes here is 10. What's the reaction here? I've got nothing going on in the x direction, so there can't be a force there. Okay, that's how to do some statics quickly. But that's not what we're talking about today. But let's do the same concept. Do something pretty simple. I don't have this in my notes, so that's fine. We'll just start off with something like this. Okay, so follow the load. Always follow the loads. Go up by 10. That lands me here. Okay, so now for this whole section, basically what I've got is W going on. I don't have any loads, so let's see what happens with W. Now, the equation I'm going to be interested in this one. The area under the curve of W is going to be the change in V. The area under the curve is nothing but this guy. The shape of this, I've actually drawn that area here. Okay, so the area is 2 times 10. This is my positive W. So I've got a negative 2 times 10. It's minus 20 going down between here and here. That's the area between here and here. So I know that I've got to go down by minus 20. Okay, that brings me plus 10 minus 20 minus 10. And then I go up by 10. And I'm back at 0, so I'm happy. That means I'm in force equilibrium. Okay, so what happened in between these points? I know I went down by 20 from here to here. Well, how do I connect the dots? Well, now I'm talking about shape. So my shape equation is this guy. Okay, I'm talking about the shape of V, so I'll look at the derivatives of V, see how they behave. V prime is W. It's negative, constant. So the slope of V is negative and constant. Should be a straight line going down. Straight line going down. Now I know how to connect the dots. Okay, that should be a straight line. Its slope is W, 2. Okay, now I want to go to my moment diagram. So I'm going to start computing areas again. The equation I'm looking at now is this. Areas of V are my changes in M. This guy, this comes at the halfway point. It's symmetrical. So it's 5 times 10 times a half. And this is a positive area, so to speak. So that's going to be 25. The units actually work out too. Foot kips. The reality check. Likewise, this is the same calculation, minus 25 foot kips. Now let's draw M. Okay, I don't see any applied moment here or here. I know I should have zeros there. From here to here, the halfway point, I know it's going to be positive, go up by positive, this is a positive area, negative area, positive 25. Goes up. We're doing here and here, 25. And then it goes down. I can see here, 25. So I'll put this in circles like I did before. Okay, so it goes up, comes down. How do I connect these? Well, I'm going to do an easy way. I combine these two. Let's differentiate the second one. V prime is M double prime, but V prime is also equal to W. So I've got M double prime is W. This means that my curvature of the M diagram is W. Okay. That means this is positive W. I've got a negative W, so I've got a negative curvature on my N diagram. Negative curvature should go like that. Okay, this is a pretty simple way once you understand it, but this is a negative curvature, right? So the sign of the curvature of the N diagram is W. Don't get this confused, please, with the sign of the curvature for the beam. This is just the sign of this graph. Okay, I think that's the simplest way to do it. Okay, now I've got my, if I followed this going from 0 plus 25, that's my maximum moment for my beam. Okay, let's do a more complicated one now. Seeing how distributed loads work. So let's do another one. Okay. Got a 10 kip here. 2 feet, 2 feet, 6 feet. I've got a distributed load here, 2 kips per foot. Reactions are, oh, this one's going down. 4 kips going down, 26 kips going up. I think this is similar. The last one, I replaced this load on the rig with a 2 examples ago with a distributed load. Okay, so that means I can probably go through this quicker. Follow the loads. -4 brings me down to -4 or 0. Nothing happens here. W is 0. W is the slope of V prime. V prime is 0, so it's a straight line till I get to here. And then I go down by 10. I'm going to give myself a little more room so I can draw the moment diagram. This goes down by 10. And then I'm at -14, as I was before. Nothing happens here. Follow the load. We go up by 26. That'll bring me to 12, I believe. Yeah, positive 12. Okay, so everything is the same as we did before. Now I've got this guy, distributed load. Okay, so let's go to our equations. The equation of interest is this one. My change in V is my area of W. My area of W is -2 times 6. That's the area of this guy. It's minus because W is defined positive going up. So -2 times 6 minus 12. I come back down 12 and go to 0. That means I'm in equilibrium. How do I connect the dots? That means I'm talking about shapes now. So this guy, W is the slope of V. W is constant and negative. Straight line going down. In particular, I could even draw the slope on it. W is negative, constant. Slope of V is negative and constant. Okay, now let's pick up the areas. We know that we're going to have to do that for the moment diagram. Okay, so what are the areas? This is -4 times 2 minus 8. Maybe use a different color. Getting a little messy here. So this area is -8. I'm putting these in boxes. This area is -14 times 2 minus 28. This guy is going to be positive 12 times 6 times a half. That's positive 36. Okay, that's how the M diagram is changing. That's this change in M is the integration of B. Integration of B is just nothing but area under the curve or area of these shapes. You don't have to do any integration. Okay, so now we've got -8. How about moment? Nothing there. I'd see an applied moment if there was something there. There's not. Moment 0. I go down by 8. Brings me to -8 here. Let's connect the dots in a second. I go down by 28. And that brings me to -36 here. Let's draw these. I'll ink these in a second. That's -36. Oh, that's a terrible color. I'm sorry about that. I guess blue is okay, but black or green is not. Okay, -8 brings me to -8. -28 brings me to -36 plus 36. And I'm pretty happy because that closes my diagram. I don't see a moment there. On this far end, moment should be 0 right at this point. If you're not convinced of that, you could just take a slice and do a moment equilibrium there. There can't be a moment there. Okay. All right. How do I draw the shape? I know I've got my points now. This is -8, -36, back up to 0. How do I draw the shape? Well, V is the slope of M. So if I'm talking about shape, now I'm talking about this guy. V is the slope of M. V, let's talk about the first portion, negative and constant. It's a straight line going down. This guy's negative and constant, straight line going down. Okay, what about this guy? It's positive. It's not constant. I'm just going to use this simple formula that the concavity of the M diagram is W, and this is negative. So I know I should draw it with some negative concavity. I'm connecting these 2 points with negative concavity. It's got to be bending down like that. Not bending in the sense of a beam, but in the sense of concavity. There's my diagram. Again, no cuts or anything. Let's do something a little more challenging. I think this sort of covers a lot of it. But let's do something a little more challenging. And no cuts. Nice and simple. Okay, here's my structure. Two feet, 4 feet, 6 feet. I've got a 6 kips here. Now I've got a linear load going down to 0, starting at 1 kip per foot there, linearly decreasing. My support here, my reactions, 6 kips, 3 kips. I'm not doing statics today. Just figure that you already did the statics, now you want to draw the diagram. It's a little ugly, 6 kips. Okay, I think we can probably move even faster now. B. Just looking at the shape and see how much room I should give myself. Okay. B comes up by 6. That leaves me at positive 6. I'm doing the changes in circles. Nothing happens now. W is the slope of V. W is 0. Slope is 0. Just comes across, it goes down by 6 when I come to this load. Minus 6. Okay, I'm at 0 there. Just following the loads. Nothing happens. Just happen to be along the 0. And then I'm coming here. Okay, so I'm starting at 0. What is the, how do I do the shear now? Okay. That is, I'm looking at V and the changes in V, trying to get to one place to another. The change in V is the area of W. The area of W is nothing but a triangle. So this is 6 times 1, and this is negative 6 times 1 times a half. So it's minus 3. Okay, the units actually work out. That should be 3 kips. Kip per foot times, let's see, kip per foot times feet. That gives me kips. So actually, the units work out for these, which is interesting, as they should. Okay, so I know I go down by 3. And that brings me to minus 3. And then I'm going to end up going up by 3. And that brings me to 0, so I'm pretty happy about that. That means I've satisfied moment equilibrium, by the way. Or sorry, force equilibrium, if I didn't mention that already. How do I draw this guy? Okay, so now I have to get into something a little bit more complicated. It's not too bad. But just have to think about it. Okay, so I'm talking about shape here. So shape is this one. W tells me the shape of V. Okay, W is the slope of V. So let's look at that. W is the slope of V. So what is W? Well, W goes from, I'm going to call it a big negative to a smaller negative. So this is W. Big negative, smaller negative, and then 0. Big negative, small negative, 0. And that's also V prime. Okay, so how do I represent that? So this is the same thing as V prime. So I know the slope is a big negative, small negative, 0. Big negative slope, smaller negative slope, 0 slope. Okay, that's how I get this shape. You could have done the same thing with the moment diagrams, by the way, earlier. But I figure the concavity is just a nice argument and it's quicker. Okay, so what does this mean? Well, at least the slope here, I know is 1. Slope of V is W. And it's going to be 0 over at this end. So that's why I'm drawing it flat. So in fact, it should be tangent here. The detail probably doesn't matter too much. Okay. Let's draw the moment diagram. We'll play a trick to wrap this guy up. Well, to draw the moment diagram. Okay, I'm going to use the areas of V, just like we did before. This is positive 6 times 2 is positive 12. I'll leave that for now. Start at 0. I don't see an applied moment. There's no fixed end or anything like that either. Can't be a moment that lives here. So I go up by 12 to this point. That's the change from here to here. Up by 12, positive 12. Now should I draw that line? V is the slope of M. This guy. And V is positive and constant. Positive constant. So that's why I left these guys here. I can just use them all the time. Okay. So what happens here? Well, there's no area here, so there's no change. The other way to argue that too is that, well, V is the slope of M. V is 0 here, the slope of M is 0, so it should just go straight across, which is the same thing as saying that there's no change. Okay, so I'm still at positive 12 over here. Okay, now we've got something tricky. I don't want to compute this area. Okay, we'll use a trick for this one. Okay, I'd avoid trying to compute areas like this. There's several reasons to avoid it. But this may not be a pure parabola. That's one reason. I won't get into all the details, but a lot of the time there could be a part that's linear, there could be a part that's quadratic. Okay, then you're trying to integrate something that's purely quadratic and it's not. Okay, I don't think you have to get into all the details, but I avoid computing areas like this because I don't know if it's a pure parabola. I think I do in this case, but I'm not going to rely on that. Okay, so let's avoid it if we can. I know it goes, this is negative. What else do I know? I know that this is going to close. It's assuming I did my statics right. So I know, well, this is going to come to here. I got a negative change. That looks good. So I'll cheat a little. I'm not really cheating that much, though. So how do I connect these points? Well, I must figure that this has to be minus 12, by the way. All right, that's the only way it'll go to 0. So it has to be minus 12. Okay, now how do I draw this? Same deal as before. Okay, V is the slope of M. V is small negative, bigger negative, bigger negative. Okay, V is M prime. Okay, I'm going to get rid of this next part, or this part I just wrote, so it's not confusing. Okay. M prime is V. So here is 0, that's why the slope is 0 here. But now it's a small negative. Bigger negative, bigger negative. I'm looking at the value of V. Okay, the value of V, small negative, bigger negative, big negative, biggest negative, I guess, which is the slope of M. So I'm going to draw a slope with a small negative, then a bigger negative, then a bigger negative. It's got to be like that. The other way, you could figure, right? So this was the small negative, bigger negative, biggest negative. That's the value of V. V, V, V. The other way that you can figure is what I did before. And W is M double prime. It's negative. Okay, this is the other way to draw the shape. W is the concavity of the M diagram, not the beam, the M diagram. It's negative, should be going like that. So let's double check and I figure I did it right. Okay, I think I'll do one more. I forgot to time this. Let's do a kind of a challenging one. Okay, I'll give myself a lot of room for this one. I'll throw in a bonus thing where showing that we might actually need to cut it for some cases. Give myself a lot of room for this. Let's do something pretty challenging. Well, it's challenging if you haven't mastered this, that's all. But challenging in the sense more involved than the last couple examples. Okay. Some wonky loads I'm going to put on there and see how we handle it. Let's give ourselves a lot of room. Okay. Got a load here, 5 kips. Got space here. This height is 2 kips per linear foot. Got a reaction here of 11.2 kips. And I've got one more force, 4 kips. This is a free end. Here's another reaction. This is minus, it's 3.2 kips going down. Okay, dimensions, 5 feet, 4 feet, 9 feet, 5 feet, 5 feet. Okay, sorry, this is so complicated. Usually I give handouts in a class day. And you can pause it if you want to copy that. Okay, where do I start? Well, I'll start where we always start, shear diagram. And I'm going to follow the loads. Let me see what this looks like. I think I gave this on the final, maybe. It's not that bad. Okay, this is V. Follow the loads, go down by 3.2. That leaves me 3.2 there. W is the slope of V is constant. Yeah, now I got some space to write some of this stuff. V prime is W, or sorry, and 0. So my slope of V is 0. That's why I'm drawing it like that. Then I go up 5 kips. This is down by 3.2. That landed me at 3.2. I go up by 5. That lands me at 1.8. Okay. W is the slope of V, which is 0. So it's a flat line going across, nothing happens. Oof. Now I've got something tricky here. I know the net change from here to here is going to be the area of W. So this guy, the area is 2, -2 times 9 times a half. And that's -9. I know it goes down by 9. Okay, I think that's okay. Down by 9, that's -7.2. Connect the dots in a second. Up by 11.2. That leaves me in the positive range again. And that value is 4. I've got no W over here, flat line going across, down by 4. I close. I'm pretty happy about that. That means I didn't make my statics right. Oh, this is 0. Okay, now let's look at this guy. How do I get from here to here? Well, this is I think we had this in the last example. V is the slope of, sorry, W is the slope of V. Okay, so I just look at the value of W. 0 here goes to small negative, a bigger negative, And that's my slope. My slope is 0. I can just exaggerate it. Why not? Small negative, bigger negative. That's how I know how to connect those guys. Okay. Now my M diagram. This is all negative, so draw it all negative. Give myself some room that way. Okay. I've got no moment here, no fixed, no applied. It's got to be 0. Nothing on the left side. Okay. Now let's compute our areas. Okay. Looks like we might have to play a trick here. That's fine. Our areas, minus 3.2 times 5. Ends up being 16 minus 16. Put it in a box. The areas, this will be 1.8 times 4 plus 1.8 times 4. And that's going to be 7.2 plus 7.2. I'm going to leave these plus minus. We'll play a similar trick as we did before, and we'll look at this guy and use the fact that we know it closes. Okay, so this is positive 4 times 5, positive 20. Okay, that way I can figure how the diagram ends up going. Okay, so most of this is the same. I just threw this little wonky thing in there. Here to here minus 16. That brings me down to negative 16. How do I connect it? V is the slope of M, negative and constant, straight line going down. So why don't I throw that on there? V is the slope of M is 3.2, negative going down. Okay. Now I've got a positive change of 7.2. That brings me to 8.8 minus 8.8. Okay, how do I draw that line? I've got a positive constant V, that's a positive constant slope of M. It's a straight line going up. All right, now I've got some tricky business here. That's, oh, I should draw this. This goes up to here. This is 8.8 minus. Got some tricky stuff here. Trying to sketch out what that looks like in a second. I know it's going to go up, and then it's going to go down. I'll fill in the details there in a second. Okay, so like I mentioned before, I wouldn't try to compute these areas if you can avoid it, which we'll see we can. I know in the end it's going to go up by 20 and close the diagram. So at this point, from here to here, the net change is positive 20. And I know I don't see a moment anywhere. So that's this guy. Bring me there. I don't see a moment anywhere. I know it's going to close the diagram. So I've got this. How do I connect them? Well, first of all, it changes it by plus 20. So that must be minus 20 plus 20 to make 0. How do I draw it? W is the slope of, V is the slope of M, positive and constant, straight line going up. Just to emphasize that point, this should be 4. That's the value there. This was 3.2. This is 1.8. If you like to put in these details, I'll just put them in there just to hammer the point on about the slopes. Okay, how do I draw this guy in between? I know it goes up, and then it comes down. How do I draw this? Well, easiest way is using W, it's the concavity of M. So I know that my M diagram should be concave down. Anytime I have W going down. That's the easiest way to do it. Quite draw this, right? This should be a positive change. So there should be a peak here, actually. But that, I still didn't draw it quite right. This should be a maximum. Okay. There we go. Okay, it's a maximum because V prime is 0. So, or sorry, V is 0, so M prime is 0. That's where you have a max. Okay, so the only strange thing about this one was, well, I wanted to avoid these areas, so I did. Let's see. I think I'm probably out of time. I was gonna cut this guy open and see maybe like what this point was here, but we'll skip that for now. I really just wanted to talk about how to draw diagrams today, so that's about as much time as I thought I should spend. I hope this has been enough examples to help you out. Of course, this is really a crash course. We'd be doing a lot more examples in an actual course, so I'll stop there and leave it at that.